Okay, last day, this was our main theme. And the key was, is that right? A1? Yeah. The key in this case was, it was not only homogeneous, but these guys were constant coefficients. The next thing we do, the next major technique we learn of solving these types, those are going to be polynomial coefficients. So they're constant coefficients, which led to the auxiliary equation. Everything was good, right? It was wonderful. So it led, we saw, if we said we're going to assume the solutions of the form e to the mx, then we saw that this ended up producing this simple quadratic, which could have two reals, one repeated real, or two complex, and then we learned how to answer those. There was nothing complicated. Was there even any calculus in this problem? No. I mean, literally, it was remedial algebra. And you should love that because it was just so clean. So what could we possibly add to this problem today? Anybody want to guess?
Function.
Yeah, not zero. Function.
Oh no.
So here's the deal. We still start by solving the homogeneous equation. Those in linear algebra, you remember when you were solving systems, right? You've always had the homogeneous, but then when the numbers weren't zeros on the other side, you also then had the particular, but you still started with the homogeneous. And every time you solved and parameterized, the homogeneous solution was right there in front of you, but then you had a second solution. So what we're going to do is still find the homogeneous solution, but then find a particular solution that satisfies this one, and therein lies the trick. Okay, so yeah.
The A coefficients, A2, A1, A, no.
They are scalars.
They're still scalars.
And for now they're reals. Do they have to be real in the long run? No, but it just makes the quadratic formula a little uglier. It still works. Your quadratic formula works whether those are real numbers or not, but it affects things like the discriminant. So for now, these are going to be purely real coefficients.
So the only change is on the other side of the equal.
So we're now throwing the other piece in. So let's do it. Let's start with something really simple. So let's say we have this. So the first thing we're going to do is solve the homogeneous equation. Which means, so let's start with the auxiliary equation, which in this case would be m squared minus 4m minus 12 equals 0. I'm going to factor it whenever I can. This is easier, right? So minus 6 plus 2. Be mindful through this section. It is amazing at this level of mathematics. You guys are at the top of the food chain, but you're still going to make plus or minus errors just as common as the remedial algebra students are, right? A third of us already have the wrong ones probably. So you got to go slowly because you can't afford to make a mistake here. So m is 6 or negative 2. Therefore, my first linearly independent solution is this. My second one is this. My homogeneous solution will be the linear combination of those two. We will get to that. I don't need to state that yet, but I will state that at some point. Now, what's going to solve this problem? Well, I'm not a rocket scientist, but I play one on TV, right? So I'm guessing y is going to look a lot like that. In other words, how can I possibly combine or cancel anything that gives me an e to the 5x unless I'm using e to the 5x? Multiples of it at very least. So what we do is we say, we're going to call our particular solution constant e to the 5x. Because I believe the nature of the solutions are going to look like that guy. I have no idea what that coefficient would be, but I think that's what the solutions are going to look like. So if that's true, then this would be 5a e to the 5x, and then the second derivative would be 25a e to the 5x. Now let's take these three, substitute it back into the original problem, and then that gives us something that looks like this. 25a e to the 5x minus 4 of these, so minus 20a e to the 5x minus 12 of these, and that whole thing is supposed to equal e to the 5x. So what do I have on the left side? Anybody?
Can we just divide out e?
No, just add up the left side.
Yeah. You get 3a. No.
25 minus
That's
20
wrong.
minus
Negative
12.
eight.
How about negative 7? Will that work?
Ooh, I can't math.
Will this work?
That's impossible. Oh,
Are we good with that?
dude, I can't even remedial algebra.
So negative 7 e to the 5x equals e to the 5x. Little drum roll, please. So that means that negative 7a must equal 1.
Yes. 1/7. Oh.
So I'm just equating coefficients. So therefore, a is negative 1/7. We have just discovered our particular solution. It's exactly this times that. Now, what therefore is the answer? I'll write this. The answer is usually stated in this form. The homogeneous plus the particular. The homogeneous is where I have the arbitrary constants. I can find them if given an initial condition, which you sometimes have, you sometimes don't. You don't worry about it. Remember, if I give you an initial condition, that's just one more arithmetic step. It's not really a calculus thing so much. So the answer to this question will be c1 e to the 6x plus c2 e to the negative 2x minus 1/7 e to the 5x. Now here's my money back guarantee. If I take two derivatives of this and then one derivative of this and put the proper coefficients, this part will completely cancel out of the problem. Why? Because it's the solution to the homogeneous. And then this part will give me the last piece. So why do I need all three? Because any multiple here will satisfy that problem. That's why I need both of these. So this is the general nature. So this new technique, which really isn't anything new, it's just like one additional step. This is called the method of undetermined coefficients.
Wow.
Were you thinking of something else?
For real.
Sorry?
That was real, yeah.
The method of undetermined coefficients, because my coefficients are undetermined when I start. You're not worried about the homogeneous coefficients. I would need initial conditions for those, but the last one will always be a simple constant. Okay, everybody cool with this? This is the next thing. So there's several types of problems, and there are some tricks and some pitfalls along the way. So we want to look at every version of this.
Imaginary.
That's actually not going to, because we know that sine and cosine are involved if I have imaginary roots. That's really not, that's not a thing to worry heavily about.
Just jumps against it.
Okay, next one. I've got, you notice I've been doing a lot with the lead coefficient of 1 just because I don't want the factoring of the auxiliary. Yeah, I can do one that's not a 1, but yeah, that means we've got to spend another minute on the algebra part. Okay, so we've got, let's say, plus 3 dy dx, and that's going to equal, or not equal, let's say minus 18y, and that's going to equal, let's say, sine x. There are rules. The rules are on the right side. There's an infinite number of functions. They can be any version of sine, cosine, e, or polynomial. That's it. There's an infinite number of variations of those, but that's it. Does that sound familiar? Isn't that kind of like the nature of all of the problems we've been dealing with? I can have anything with an e on the right side, anything with a polynomial on the right side, anything with sine or cosine. Aren't there other functions that I could technically put on the right side? Yeah, like tangent, secant, natural log. That is the next technique we're going to learn. That's Wednesday's lecture. That's a more complicated technique. But for the big four right now, sine, cosine, exponential, polynomial, which is, it feels like that's the nature of most of our answers anyway. Okay, these are all the ones that are going to work. Oh, good, it's got some juices. So let's start with the auxiliary equation. This should never be hard, but don't go too fast. I will actually have people try to do this in their head and give me the answer, which is great, and almost all parts of that are usually correct except for the signs, because we miss them up.
So, so what you said is, if you see like the big four, like the sine, cosine, exponential, and the logarithm, then do you...
No, sine, cosine, exponential, and polynomial.
Okay, if you see those four, then you use the method of undetermined coefficients.
Right, which is
Then-
all we're gonna see today. That's all we're gonna look at today. But those clearly can't be the only things I can have on the right side.
And then
So
if
if I have
it's like-
something else on the right side, then we will need an additional technique.
Okay.
And then that would be sort of like all of the rest of them, but that's a more complicated technique. Yeah, Patrick.
This is just, like you said, just solving those situations where you're equal to.
Yeah, that's all we're doing today is we're doing one of the big four on the right side. Because again, they're probably the most common ones that we're gonna see. So when I factor this one, what does this factorize? M minus 3. So m is -6 or +3. So I'm gonna just go ahead and state them right here. E to the -6x, e to the 3x. And I know what my homogeneous solution is now, piece of cake. So now, this is not a trick question, this is a tricky question.
No, you got.
I'm asking you a question here.
You have to add plus b cosine of x.
Why?
Because.
You're right.
Was a general
Because
solution.
one could be represented as sine or cosine.
Well, if I take two derivatives of the sine, won't I get cosines and sines? And how am I going to cancel the cosines? I can't. So, that's exactly correct. I honestly have no idea what the answer is. I never know. I just make up the problems as I go. But if I only choose one of these, I will absolutely reach a dead end because I will have sines and cosines that won't all cancel.
The exponential is there because that's part of the general solution, right?
It's part of the homogeneous solution. The whole thing is the general solution. So the homogeneous and the particular. The homogeneous we always do first because it's the least, right? It's the easiest part. And it's part of the whole answer. And it is a very important part. But it also has, we're going to see, has something to do sometimes with my choice here as well. All right? So I need the whole thing. That doesn't make this harder, but it's more like if I leave something out, then it's not going to work. So let's do the first derivative. So a cos minus b sine. And then the second derivative, negative a sine, negative b cos. So as long as I don't go too fast, I'm going to be gathering terms. Tell me about a and b. What do you think we're going to see? What do we see over here? Not the negative part, but the
Fraction.
probably fractions because my coefficient on the right side was just a 1. But I got to have all these other things cancel. So probably. It's unusual if you did this and you didn't get fractional coefficients. So everyone says, oh gosh, I got these ugly fractions, I did it wrong. No, you're going to get fractions. How ugly they are, I don't know. That depends on other things. But so when I plug these in, I'm going to have this guy, negative a sine x, negative b cos x, plus 3 of these. So plus 3a cos x minus 3b sine x, and then minus 18 of these. And that whole thing has to add up to, where is it? Has to add up to sine. Not a sine, just the right side. Because what I did was I said, here's what the y looks like, so I do all my derivatives, I stick them on the left, it's got to add up to the right.
It should really equal sine x plus 0 because we have to get
Okay. Okay, sine x plus 0 cos x, we can do it that way. We're going to see that's going to fall into our lap anyway. So, what do I do now? This is really complicated.
The sines and the cosines.
Okay, rather than combine the a's and b's, let's combine the sines and the cosines. That might be a little safer. So I do this for me. Okay. Add up all the coefficients for the sine. So I have negative a and negative 18a, that's negative 19a. And then I have negative 3b. How does that look? Now let's add up all the cosines. So we've got that, and that, and that. So how many a's? Looks like I have 3a. And then how many b's? Negative 1, negative 18, so that's negative 19 b's. I'm going to put it like this, plus cos. All right, I guess I can put it, you know, I'll put it here. Might read better. Okay. Now what does this all add up to? How about if I write it like this? 1 sine plus what?
0.
0 cosines. Why would I write it that way? Because now I just have to equate coefficients. That has to equal 1. That has to equal 0. You don't have to write it like this, but I like that suggestion that you had. Because now I can't stumble on the... If I didn't write anything here, then it's less
hard for me to
obvious.
figure it out. I was like, what the heck is happening? How are you canceling out like half of the equation? Well, because it equals 0.
But does everybody understand? If I don't write this, it's not completely obvious what I'm going to do next. But oh, the sine on the left equals the sine on the right, the cos. So this produces 2 very simple linear equations in A and B. Any ideas? There's actually 6 ways you know. One of them's graphing. We're not going to do that one because we never read the solution. I can use a matrix. I can use Cramer's rule. That actually might be the fastest. I can use an inverse of a matrix, or I can just do substitution, or the easiest one, I can just do the addition method. Remember that? That's where you add them to eliminate a variable. So if I do that, let's say I want to get rid of the b first, then I would multiply this equation by 19. And what would I multiply this one by?
3.
Negative 3. Yeah. I don't think I'm going to mess up the right side. Okay? So on top I'd have negative 361a, negative 57b equals 19. And down here I'd have negative 9a plus 57b equals 0. So what have I got? Negative 370a equals 19. Does 19 go into 370? No. So a equals negative 19 over 370. Ooh. Now I have a couple choices. I can take that, substitute it back in and solve, or just do this again. I'd rather just do this again. You never take your old solution and substitute it back in. That's like the most amount of work humanly possible, but that's what all the algebra students always want to do. No, just do this again. Keep these guys as integers as long as you can. So now I want to get rid of the a. So if I multiply this equation by 3, then I'm multiplying this equation by negative 19, just like the other side. I'll do it over here. So now I have negative 57a.
Wait,
Negative, did I need?
those ones are opposite signs. So
Oh.
Positive.
Thank you, thank you. Yeah, that should be a positive. Good catch. That might not have worked so well. So negative 57a, negative 9b equals 3, positive 57a minus 361b, and that equals 0. So negative 370b equals 3, so b equals negative 3 over 370. That's pretty ugly. They do have the same denominator. I guess that's a good thing. I'm pretty sure I did this right. There's multiple ways I can check. I can check the coefficients, and this is what I do in a baby algebra class. This is the easiest. Did I bring a calculator? stick him in there. So, negative 19 times negative 19 over 370 using my fraction key, minus 3 times negative 3 over 370 using my fraction key equals, and my calculator spit out a 1. That's a really good thing. Now, since I used elimination, not substitution, it would be absolutely impossible for it to fail in the second equation. If I use substitution and I have the wrong number, it will work in one but not the other. Wrong number will always check in the one you used it on to get the wrong number. But because we solve these independently, it's actually impossible for it to fail on the other one. That's nice to know. I can't prove that in this class, but it's because of the way we solved it. So can I be certain of those coefficients? Yeah. And by the way, that check was really hard, wasn't it? You always check your answer. What is the final answer then? So, the final answer, go all the way back to there. C1 e to the negative 6x plus C2 e to the 3x. Now I throw these guys in. Minus 19 over 370 sine x minus 3 over 370 cos x. We don't love the fractions, but anytime you're doing the sine and cosine, you're always going to get fractions. The only way I could have avoided the fractions, anybody want to tell me? One change to the problem that would have avoided fractions.
Multiply through by.
No, 370 is my coefficient there. That's kind of cheating though, isn't it? Then I would have got nice integer coefficient. That's basically the only way to avoid the fractions. You're always going to get fractions. Sometimes you won't because of the choice of the original coefficients. Now, this technique is sound. The most common error on a problem like this is not doing both the sine and cosine. This, by the way, of all the problems, this is probably my least favorite, just because I know what it entails. There's no way around it. You're always going to do this.
So if there's a cosine, we also have to have the sine.
If it had been only a cosine, we'd have done the same thing. Yeah, that, you know. And by the way, there are situations where one of the coefficients can be 0. I want you to think of partial fractions decomposition. When you had the irreducible quadratic, you always said, well, I'm going to go ax plus b over my... Well, either the a or the b can be 0. They both can't be. But the problem is a lot of people just put a over. And it turns out I needed the x term and now it's not going to work. But if I do the ax plus b and the a ends up being 0, that doesn't cause a problem. But if I leave it out when I needed it to be there, I'm never going to be able to get it. If I left this out, I never would have been able to finish this. Is it possible that I could have a problem where one of those ended up being 0? Yeah. All things are fair game. What you can't afford to do is leave out something that might be in the answer, because now, high probability it won't work at all. Yes?
So if it was equal to cosine instead of sine.
You'd have done this exact same thing. Exactly the same thing. In fact, what if you had a sine and a cosine on the other side? Well, that makes it easier. Yeah.
What if it's 10? What if it's...
That's what I was mentioning earlier. If it's not one of the big 4, that's the next technique we're going to learn. All of the rest of the things. You know, what if it's log? What if it's a square root function? You know, what if it's not one of the 4 I just said, sine, cosine, exponential, polynomial? We do have another way. It's more complicated than this. We'd rather use this if we can. But if it's not one of those 4, I can't use this. Why? Because only sine, cosine, e, and polynomials, in a sense, look like their own derivatives. Well, polynomials don't, well, it's still a polynomial. Right? Sine, cosine, give me back sine, cosine. E's, give me back e's. Oh, so if that's a tangent, right? The derivative doesn't look like tangent. Does that make sense? If it's a log, the derivative doesn't look like log. That's why, that requires a completely different technique. John?
So that's always going to be the particular function, a sine x.
Well, because I have a sine.
Okay, yeah.
Yeah, that part depends on what this is. I said there's 4 possibilities. Yes. So what have we done so far? We've done an exponential. We did a sine. We're going to do a polynomial. Let's do that one next.
I have a quick question. What if the answer is sine x plus e to the x? Can you do like a combination of those things?
Well, isn't that what that is? Oh, I'm sorry. You're talking about on the right side.
Yeah.
Exactly. Yeah, you're now one level higher, so let's hold off on that. But yes, you're absolutely correct. So I kind of want to do these piecemeal. We'll do kind of one at a time. So let's take another one, relatively simple. Let's do, let's put a generic polynomial over there. Oh, I'm sorry. My bad. I don't want that. I want that to be a y. Sorry. What am I thinking? dy dx. Come on. I told you I was kind of in a fog today. Sorry. I want this to be real simple. So my auxiliary equation is going to have what kind of roots?
Complex.
Or even go for
Imaginary.
purely imaginary, which means that my solution will be
Sines and
sine cosines. We love those. The mixed ones, you don't like as much. 3 plus or minus 2y. I don't like that one as much because that answer is so much harder to work with. Purely imaginary versus purely real are about the same level of difficulty. Okay, so my auxiliary equation, m squared plus 4 equals 0. So m equals plus or minus what? 2i. So my linearly independent solutions are, careful now.
Wow.
Where does the 2 show up?
inside the sine and cosine.
It's the argument.
Yeah.
If it helps you think of it this way, technically isn't this 0 plus or
Right.
minus 2i? Oh, so it's e to the 0x times the cosine, e to the 0x times the sine. That's why it's purely sine and cosine, because it's a purely imaginary solution.
They're both, isn't one supposed to be sine? Or are they both?
Oh, yeah. Sorry. This one here is friendlier than most. We like this one. Okay, so there's my homogeneous as a piece of cake.
Wait. It's not e to the mx?
Well, yeah, but so what happens when these are imaginary?
It turns out to e squared and then there's a cosine 2x plus sine x, right?
Well, remember, is it alpha plus or minus beta I? We went through the whole derivation,
Yeah.
and you get that.
Oh.
Otherwise, you're getting e with an imaginary exponent.
That's y1, y2. I'm going to h or y8.
Remember, if we don't want to write e with an imaginary exponent, we want real functions. So we showed last day that if it's of the form alpha plus or minus beta I,
You're like skipping some steps, right?
yeah, but you can always go directly to this. A reminder, when m was, then we know the solutions are of the form, what? E to the alpha x
Times
times what?
e to the I beta.
Well, times cosine
Right.
beta x plus I sine beta x. You guys remember this? We did this big derivation.
Yeah.
But then when we messed with the coefficients and did all that, we got back to here. So just go directly here. You have no choice but ugly when it's something plus or minus 2i. Now you have the e and the sine cosine coexisting.
Well, what about the e squared though? I
E
guess that's
squared?
Yeah,
no.
because e to the alpha.
There's no e squared.
Alpha zero.
Alpha is
It's either the 0.
Alpha zero, I guess.
Yeah, the two is the beta, if you will, and that goes in the sine cosine.
I missed the zeros.
Yeah. Okay. Now, our particular. This was supposed to be something. Well, it's polynomial of what degree? 3, 4, 5, 6. How do I even know where to stop? Hey. Okay. Let's just say we pick a large degree. Then you have derivatives of degree 1 less. Agreed? So let's just say for fun, you pick 10th degree. So my second derivative is 8th degree, my first derivative is 9th degree, my original function is 10th degree, and I add and combine terms. Won't I get an answer that's 10th degree? Oh, does that kind of put an upper limit on what my yp can be?
Yeah.
Yeah. Can't be bigger than that one, because derivatives of that will get smaller, but that's still going to show up here. Have we got that? So what am I going to put then? So it's just x cubed?
A squared plus b x squared plus c plus
I got to consider everything all the way down. Is it possible some of those coefficients can be 0? Yes. In fact, it's very likely something can be 0, but don't ever start by assuming, because that might not actually be the case.
Question.
Yes?
If the x cubed itself had some particular coefficient in it already, would we still just write ax cubed?
Yes, yes. I've erased way too much. My original sign had a coefficient of 1, but what if my original sign had a large coefficient? Well, then it would just counterbalance when I was solving for the a's and b's. Why? Because remember we set them equal to the 1. Oh, so if my original sign had a large coefficient, we would have set it equal to that coefficient. So I did not put a coefficient, but if I put anything here, this is still the form, but it would change what A, B, C, and D are going to be because they have to now satisfy a different constraint there. So let's do it. So the first derivative, which I'm not actually going to use in the answer, is 3a x squared plus 2bx plus c. So this will be 6ax plus 2b. Does that look right?
Yeah.
Okay, I think I got that right. I'm doing second order right now, but we could go higher order. That's not a problem. The problem with the higher order, was because it might have made this one harder, but we did some last day, remember where we got roots of zeros? That made it really easy. So there are no rules on what you can do, but you're only going to see things in general. Only down here. Where did I hide my eraser? Oh. It's like my grandmother when she would misplace her glasses, they were always hanging on her neck. Yeah, I know, it's sad. Okay. You guys do know I locked myself out of my office this morning. You know, that's how my day started. Okay, so let's put these in there. So I've got 6ax plus 2b plus 4 of these. So plus 4ax cubed plus 4bx squared plus 4cx plus 4d. And all of that has to add up to what?
X cubed.
X cubed. So now let's gather terms. Let's see, how many x cubed terms do I have? Just one. So I have 4ax cubed, and I think I have just one x squared term.
All the other stuff doesn't even matter.
It does to a degree, it really does. And then how many x terms do I have?
2.
So what is that? That's
6a
6a plus 4c times x?
Yeah.
And how many constant terms do I
4b
have?
plus 2.
Plus, we'll call it 2b plus 4d.
But the only thing on the right that has a term is x to the third.
That's true. Which means the sum is 0.
Oh, yeah.
That doesn't mean that either b or d are 0. This sum is going to be 0, but it doesn't mean that a or c are 0. None of them are. Well, some of them might be. We don't know yet. So we don't want to try to do this too fast in our head. How about if I write like this? Would that be useful?
Yeah.
Yeah.
So let's equate. Okay, it's a good one. So I've got 4a equals what?
What?
I've got 4b equals, I've got 6a plus 4c equals 0, and I have 2b plus 4d equals 0.
Just
All right, well the first two are freebies, aren't they?
Yeah.
So the first one says that a is 1/4. The second one says that b is 0. Let's fast forward to line 4. B is 0.
So D was
So D is 0. A is 1/4. So C is
negative 6 over 16.
So what is C?
Negative 6 over 16.
Or negative 3/8?
Mm.
It's not 0. Ah. Now, was that hard in general? No. When we solved for the A and B with the sine cosine a moment ago, it's the same sort of low-level algebra, but I am technically solving a system of 4 variables, 4 equations. It's just the A and B were automatic, so it made the C and D more or less automatic. So now, when I write the final answer, y equals, okay, so go back to the beginning, it's going to be C1 cosine of 2x plus C2 sine 2x. A was 1/4, so plus 1/4 x cubed. And what was C? C was the x
Negative.
coefficient. Minus 3/8 x. Now that one seems kind of odd, the last part. But think of it this way. When you take 2 derivatives of this, what are you going to get? When you take 2 derivatives of this,
6.
you're going to get 6/4.
Yeah.
Oh, and when you, well, so when I take 1 derivative of this, I'm going to get 3/4 x squared. Right? It's the second derivative that I need. So I'm going to get, what did we just say? 3, so you're going to get 3/2 x. That's what you're going to get when you take 2 derivatives. And then you're going to add that to 4y's. And 4y's will be a whole x cubed minus 3/2 x, and that cancels with the other 3/2 x and leaves you just the y cubed. So do you see if I check this, it will work perfectly. By the way, if I only checked this, if I only had that much, would it work? No. I'd have an extra term left over. So this is the general solution. The particular was a little bit of work here. Polynomials you don't necessarily love because you have to have every term in descending order. Now, question I got asked, what if we start mixing terms? Actually, that's not a complication at all. What if I had done, let's just do it right here. What if I had done that? What would you do here?
I guess you have a letter.
You'd do that, and you'd follow through exactly the same way, and the E coefficients would take care of themselves, because they will not be in any way related to the polynomial coefficients, are they? They're not going to combine or cancel. So if I have mixed terms, I just represent everything. That's actually fairly simple. That's not the case that gives us the most trouble. It's longer, yes. It is a longer problem when if I write e to the x plus cos x. Oh God, there's a lot of work. No way around it, there's a lot of work. Okay. All righty. Okay, this one seems pretty harmless, and it is. You know something's up. That's the whole left eye thing. I never wink with my right eye because right eye winks are boring. It's the left eye. If I do a side eye, I might go right, I think. Not in general. Okay. Go slow. This is the one spot we cannot afford to make an error. This one's easy, but we get it. I don't say it jokingly. The only error we're going to make is switching the signs. So, y1 equals e to the 3x, y2 equals e to the negative 2x. Well, that was easy enough. All right, so now my yp is going to be a equal a to the 3x. This one seems pretty simple. So feels like the first one we did, I know. So 3a e to the 3x and d squared y, x squared is 9a e to the 3x. Okay, beautiful. All right, so let's put these back in the original equation. So I've got 9a e to the 3x minus the derivative minus 6 times the original function. Where's e to the 3x? And of course that equals e to the 3x. And so when I combine these guys, they add up to They add up to,
Zero.
Houston, we have a problem. That don't work.
Nine out of 1.
No, they
It
add up
should
to
be,
zero.
and the YP is supposed to be x e to the 3x.
And why would that be?
Because y1 is e to the 3x.
Beautiful. That's 200 miles. That's easily worth 200 miles. Yeah, you're on it today. I said the one that gives us issues is the repeated solution. But I already know what to do with repeated solutions. I just add an x. But our repeated solution came from the particular. That's already there. That's the one I was referring to when I said the repeated solution will give us issues because we're not looking for it there. So what I needed to do was do what?
X e to the.
How about-
X a?
AX. It's still a repeated solution. The fact that it came from the particular is irrelevant. It's still, e to the 3x solves the homogeneous. It cannot also solve the particular. That would not be possible. So here's a situation where I snuck one in on you. So this is not going to work, what I have in front of me. So I got to use a little product rule, right? So first times derivative of second, I'll write that like this, plus second times derivative of first, first times derivative of second, plus second times derivative of first, and that'll happen twice. So this is then 9ax e to the 3x plus 6a e to the 3x. Now let's try this and see if this works on the original statement of the problem. So I'll put the second derivative in, 9ax e to the 3x plus 6a e to the 3x. Now I want, where is it? Minus the first derivative. So minus 3a x e to the 3x minus a e to the 3x, and then minus 6 times the original function. And this is all supposed to equal what? It's still supposed to equal this. But shouldn't it equal x? No, there's no x on the right side of my equation. There's only an x in my particular solution. So this is still e to the 3x. Now, does anything combine or cancel? Well, let's go after the x terms first. Do they cancel? Yes? Right, the crowd goes wild, confetti everywhere. No, that's cause for rejoicing. That means this is going to work. Because on the left side, I don't have any x's. So what do I have left on the left side? 6a minus 8, so that's 5a e to the 3x, and that's supposed to equal e to the 3x, so a equals what? 1/5? Beautiful. So we figured it out. So our particular solution is simply 1/5 x e to the 3x. This would not have worked if we didn't throw in the x. What if you have a second repeated solution? You remember what to do?
X squared.
Actually, yeah, you just keep going. That's not an issue. It becomes an issue when I got to take all my derivatives, maybe. I don't know. It still's never going to be that bad. So the final, let's do it over here. So the final answer to this problem then is y equals c1 e to the 3x plus c2 e to the negative 2x plus 1/5 x e to the 3x. And that's how I finish. That's it.
For that second derivative, the partial derivative, shouldn't it be 3a e to 3x, not 3
Yeah.
to x?
There's just an extra x on the.
Do I have an
side.
extra? Oh, that one right there? You're right.
There you
You're
go.
right. Because I added, yeah, you're right. Because I did combine those here. Good catch.
And then we knew
That's-
it was we knew to toss that x after the particular because it was the same thing as the y1, the final answer.
I'm not sure you need to toss it.
Or like not toss, but like we put the x. In front
Oh, we
because-
saw. part of the reason for the placement here. These are my homogeneous solutions, but wait a minute. My particular can't be a homogeneous. See, if I call my particular A e to the 3x, I know it's going to solve the homogeneous. It can't solve this and solve the homogeneous. It can't all equal 0 and not equal 0 at the same time. That's how we recognize it's a repeat. Can you have more than one repeats? Absolutely. Yeah, in fact, we did it the other day where we did higher degrees, but we created simple situations where you got m equals 0, and maybe m equals 0 with multiplicity. So if I have that, then I take that into account when I'm doing the whole problem. So if whatever I have there in the homogeneous, I see the exact same things in the particular, this is not the worst problem. There's one way worse than this. This is way worse. Why is this way worse? So now you have to do your particular as a x cos plus a or b x sine, and then do that one with some, yeah. That one's worse. Everybody understand? Because you got to do it for both sine and cosine. Yikes. Yeah.
So real quick, once we found the homogeneous solutions and we see that they're the same, then we immediately skip to our particular solution.
What if these were the same? Then we would have thrown an x in one of these, right? If I got it, if this was something squared, we'd already do it right here. So the very fact that the particular, which I'm going to identify in this form, if I don't put the x, then I'm basically saying this is also a particular, but it can't because this will make this 0. That's why I needed the x, because even though it wasn't a homogeneous, it already showed up once. So I still treated it as a repeated solution of some form. The repeated solutions don't make it harder. It means, yeah, I got to use a little product rule in my check. But if I don't take that into account, I'm going to get an answer that doesn't work. So the first time I did this and everything canceled on the left, right, that's red lights flashing. Okay, something went terribly wrong. And that's when you say, oh, it's a repeated solution. If I fudge that one, I'll have people not get them as 0. They'll add them up to something other than 0. No, you can't do that. So I got to fix that one. Okay, so far so good? All right, let's keep going. Let's keep it simple. How about
For any other problems, do we just stop at once we find A?
Well, no.
Then we do all.
Then I stated the whole answer. Yeah, so I had the whole answer. So I just wrote it on this side.
Okay.
Once you find A, there's no more work to perform.
Mm-hmm.
That's true.
Okay.
That's true.
Is that 13 or 15?
13. 15. Come on. Who's gonna do 15? That's just crazy. Okay. Let's go with. Now, at least I'm not going to get repeated solutions on this one. But this one is a little bit longer. What we'd like to be able to do when we leave today is I can at least set up any problem that has constant coefficients and the solutions on the right are one of the big 4. I might not be able to solve it exactly because it has to do with being able to solve the auxiliary equation. If it's a second degree, then I know I can. If it's a higher degree, then I have to get lucky and have a nice friendly factorization, which is pretty much every problem in the textbook. It's going to be a friendly factoring. Why? Because if I just gave you a random 3rd or 4th degree polynomial that had a constant term, that is no guarantee. In fact, you don't even know if you're going to get real solutions. That's beyond us, because that almost requires technology to be able to even start that problem, which kind of misses the point. If I have to use technology to find the roots of the auxiliary equation, I'm in trouble. No, that I don't want to use. So,
M equals 2 plus or minus 2.
So you already got it?
We have to do the completing the square and stuff.
You can, however you want to do it. Use quadratic formula. Is that going to factor? No, because your discriminant, remember the b squared minus 4ac part, that's going to be negative. So I know I have 2 complex solutions. So whether you use your quadratic formula or you just complete the square, I'm lazy. I complete the square because I have the answer then in one step. Quadratic's going to take you an absolute minimum of 3. And that's if you don't make any mistakes. So this is m minus 2 squared plus 3 squared. Yeah, it's actually that easy. Doesn't even matter if they're nice numbers. It's always that easy. So what am I? 2 plus, remember this is 0. Goes over there, plus or minus 3i. To be quite honest, I don't care how you get that. I just need you to get that. For most people, they'll just use their quadratic formula and not worry about it. Okay? But you got to get that because that means I have 2 complex solutions that have both the real and imaginary part. That's the most complicated of all the answers because that's the only one that combines things. So what are my 2 linearly independent solutions then?
e to the 2x cosine of 3
Good, cosine of 3x, and then the second one?
e to the 2x sine.
Beautiful. Everybody understand? We spent a significant amount of time yesterday deriving this result so you wouldn't have to use complex exponents. The complex exponents of 2 plus or minus 3i eventually get us to here. I'm just saying you can fast forward. You don't ever have to rederive that. Okay, that was a really, really important result. So I don't see either one of these in this, or do I? This is not a trick question.
e to the 2x.
You see e to the 2x, and then you see e to the 2x times stuff. So is that a repeated solution? No, because it doesn't stand alone. The e to the 2x would have to stand alone to be repeated. It's being multiplied by something else. You know, just to be ornery. Let's say your homogeneous solutions. Let me just say, let's say they were e to the 2x and e to the 4x, and then my particular was e to the 3x. Well, if I think of that as being e to the 2x times e to the x, and now I've got it. Doesn't work that way, does it? This is true, but it doesn't mean that I'm repeating the solution. It's being multiplied by something else. So I'm being kind of facetious here. No, it's not repeated. It's multiplied by a cosine. So therefore, there's no repeated solutions here. And in fact, the fact that this was ugly, believe it or not, has no effect on the complexity of that part. None whatsoever. The fact that I don't have a repeat automatically means it's a little less. And I don't have any sines or cosines here means it's less still. So as ugly as this one started out as, it's not going to be that bad. So we got to get this part right. What is my particular? The form is going to be what?
Ax squared
Well, I'll give it the same word. How about that? Then
plus bx squared plus cx plus d.
it is highly probable that A, B, and C are all not zero. Highly probable. Well, why didn't we get some zero in the other problem? Because remember, I didn't have a first derivative term. I only had the second derivative in the function. I have all 3 derivatives, which means that everything's going to combine at every step of the way. So, first derivative. Walk me through.
2a plus c.
And then my second derivative.
4a e 2z plus 2b.
Okay. Take our time. I've got 4 coefficients here. So I'm going to need 4 equations. All right, so when I substitute things back into the original problem, I'm going to get 4a e to the 2x plus 2b, there's my second derivative, minus 4 of these, so minus 8a e to the 2x minus 8bx minus 4c, and then plus 13 of the original, so plus 13 a e to the 2x plus 13bx squared plus 13cx plus 13d. The funny thing is, I gave you something where my coefficients here were both 1s, which sounds so friendly. But now you know as an utter assurance that all your coefficients are going to be fractional. You know that. That is an absolute guarantee. So the only way I can avoid fractional coefficients there is to reverse engineer and figure out what numbers to put here. Way too much work. All right, so let's gather terms. So I have 4a, negative 8a, plus 13a. What does that add up to?
9A.
So it's 17 minus 8, so 9a e to the 2x. X squared, I only have that one. Do I have any x terms?
Yeah.
There and there. And constant terms,
3 of
I
them.
have 3 of them. There, there, there. So 2b minus 4c plus 13d. And all of this has to add up to the right side of my original equation. Sometimes we inadvertently try to set it equal to this. No, I gotta set it equal to this, because otherwise I wouldn't be able to solve for the coefficients. Does that look right?
Yeah.
All right, let's take the gimmies. So I've got 9a equals 1, so I'll write it out. 9a equals 1, so a equals 1/9. Beautiful. What else do I have? 13b equals 1 also. Now what do I got? That must equal 0. So negative 8b plus 13c equals 0. That's a 13. Sorry. We just said d was 1/13, so I'm lazy. So what have I got? I've got 13c equals 8/13, so c is 8 over 169. And then the last statement, I'll put it up here, is 2b minus 4c, get out your calculators with the fractional key, plus 13d, that all must equal 0. So 13d equals negative 2/13 minus 32 over 169. So d equals, and I'm going to use my fraction. Okay. That should be plus. So that's a plus. That matters. All right.
Divided by 2, 197.
So what do you got? 6 over
2197.
2197. It's 13 cubed. Do we have everything we need? Do we have everything?
Yeah.
So we can now state the final answer. I'll go ahead and erase this. Maybe I shouldn't, but. So y equals C1 of these plus C2 of these. Where's A? Plus 1/9 of x squared.
No, did the 1/9 go with the e to the 2x?
Oh, did I?
Yeah.
It went with the e to the 2x up here.
Oh, thank you. I'm sorry. I'm ahead of myself. Sorry. 1/9 e to the 2x. It was the 1/13 that went with the extra. I should have erased it. Plus 1/13 x squared plus 8 over 169x plus 6 over 2197. Should I even bother worrying about things like common denominators and stuff? Nah, it is too much trouble. Just leave it like that. That's ugly, but it's correct. So does it bother us that my original auxiliary equation had complex roots? Does that matter at all on the complexity, no pun intended, of this problem? No.
It's easier to use complex roots anyway.
Well, they're very unlikely to show up as repeated roots, that's for sure.
Yeah.
The ones that, there's two problems that are going to give you trouble in general. When it's a sine or a cosine on the right, because now you got to do a sine, b cosine, or vice versa, and then you're solving a system. That one's a little bit more work. And the situation where you have repeated roots, but particularly your particular solution is a repeated homogeneous root, because that's the one that catches you off guard. We did an example, and we saw it didn't work. Okay? Everybody cool with that? So far, so good? Do these problems kind of feel like all of them are exactly the same thing over and over again? Yeah, and are we doing any calculus in any of these? I mean, taking a couple derivatives, but that's just, this is not that bad, okay? It really is not that bad. All right. Let's do one more of these. All right, let's do, I'll keep it simple. All right, I'm gonna give you a little head start here. Hear all this commentary in the background.
So there's an x squared.
So what's our auxiliary equation?
M squared minus 2m. Oh, so m minus 1.
Is that it? Everybody got that? Okay. I can deal with that. Oops. So we say 1 with multiplicity. So therefore, what are my two linearly independent solutions? Yeah. Okay, that's easy enough. All right, so now we'll start the particular. So I want a e to the x, right? Oh, it's repeated. So a x e to the x, right?
No.
Oh, it's repeated the second time. So a x squared e to the x. Oh, that was so sneaky of me, wasn't it?
Right, it was not too bad on this one.
It's only two terms, so it's not like this is going to blow up too much. Maybe a little bit.
Right, it's nice to do this.
First times derivative of second. By the way, notice all my coefficients are 1. Yeah, this is fairly friendly. Plus second times derivative of first, 2ax e to the x. My second derivative, so ax squared e to the x plus 2ax e to the x. That's the first one. And then this one's going to be plus first times derivative of second, 2ax e to the x, plus second times derivative of first. I said second times derivative of first, but I'm keeping them in the same order. By the way, you should probably do that. Don't have x times e to the x and the next term have e to the x times x, because sometimes it's harder to identify the like terms. If you just keep them in the same order like I did, it's less comfortable, but it's actually much easier in the bookkeeping. So I do get a little bit of combining, right? What combines? The middle two. We've seen that before, right? We saw that with reduction of order. Whoops, that's just x. And 2a e to the x. All right, so let's solve. So ax squared e to the x plus 4ax e to the x plus 2a e to the x, and then minus 2 times the first derivative, so minus 2ax squared e to the x minus 4a, oh, that's 4, I can't remember, 4ax e to the x, is that right?
Yeah.
I'm looking at a little seam in the board. And finally, plus, all right. What am I hoping on the left side?
Cancellation
But of what?
of the x squared and the x term.
Let's get rid of e to the x.
I'm hoping everything except the pure e to the x terms cancel, because if I have any x e to the x's on the left, then it's not going to work, is it? So, let's see. There's the x squared, here we go, x squared. One of them minus 2 and plus one of them. All right, x terms. crowd goes wild. And what am I left with?
2a.
2a e to the x equals e to the x, so a equals a half. So my final answer here is y equals c1 e to the x plus c2 x e to the x plus what?
1/2 x squared e to the
1/2 x squared e to the x. Would there be anything wrong with factoring out the e to the x in this context? Do I have to factor out the e to the x? No. I got to use this to answer a whole bunch of questions in physics where I got to enter, like, typical physics. You got to do 30 different values of x and then find the, small iterations. I'd probably factor out the e to the x just because there's less buttons on the calculator that I have to push. But that's perfectly correct. Good? All right, that's good. Stop that. I will use